Welcome to The Explainer. Today, we're diving straight into the mechanics of how large language models actually break out of their text boxes to interact with the real world. We hear a lot of talk about AI doing things, right? But how exactly does code sitting on a server actually book a flight or run a complex calculation? Well, this isn't just theory anymore. This is the exact underlying technology powering the next generation of AI, the agents that are going to be autonomously doing parts of our jobs for us in the very near future. The stakes are incredibly high, and understanding the mechanics behind it is absolutely crucial.
So, it's a really fundamental question. How does a text predictor interact with the real world? Because by themselves, these models are really nothing more than functions that take in a string of text and output a string of text. Literally, that's all they do. They can't browse the web, they can't calculate math, and they definitely cannot schedule a meeting on their own. Think about it like this. An LLM without tools is kind of like a certified genius locked inside a windowless room. They have no phone, no internet, and absolutely no way to reach the outside world. They can think incredibly well on their own, but they cannot act. To bridge that massive gap, we have to augment them.
Here's our roadmap for this explainer. We'll start with 1. Beyond text. Enter AI agents. Then we'll look at 2. The anatomy of tool usage, followed by 3. Executing the tool call. After that, we'll cover 4. Learning by example, and wrap things up with 5. Training for autonomous action.
All right, let's jump right into Section 1, Beyond Text, Enter AI Agents.
Think about the difference between following a strict recipe and being an executive chef. A system with zero autonomy is basically forced through a rigid, predefined order. It's totally hard-coded. First you search Google, then you search archive, then you summarize. It's just following a script. But an agentic system completely breaks free from that loop. The LLM acts as the brain, autonomously deciding exactly which tool to use and exactly when to use it, based entirely on whatever the user is asking for. It's navigating its environment dynamically instead of just, checking boxes.
Which brings us nicely to Section 2, the anatomy of tool usage. Using a tool isn't just one magic click. It's actually this highly coordinated 5-step process. It requires careful orchestration between the human developer, the LLM, and external computing systems. First, a developer has to create the tool. Then, they define it for the LLM. The LLM must then select it, call it, and finally, process the output. And here's why this is so important. If any single one of these steps fails, the whole shebang breaks down. If the AI hallucinates a tool name during that selection phase or formats the request even slightly wrong, the action just crashes completely. So how do we even explain a tool to an AI initially? Well, in the tool definition step, we feed it a highly structured JSON schema right inside the system prompt. We're explicitly telling the bot, hey, you have a tool called multiply, and it takes 2 numbers, A and B. We are spelling out exactly what parameters are required so the model knows the precise rules of engagement before the conversation even starts. Okay, let's actually see this in practice in Section 3, executing the tool call.
Now, here is the great secret behind AI agents. It's kind of an illusion of autonomy. When the LLM decides it needs to multiply those numbers, it never actually runs the code. It is fundamentally incapable of doing math itself. It's honestly a bit like a highly confident but mathematically inept middle manager. It just delegates. It outputs its intention to do math, formatted as a JSON object, and forces a custom external script written by a human to do the actual heavy lifting.
It creates this perfect loop. The user asks the question, the LLM selects the multiply tool and generates that JSON intention. Then our external system intercepts it, actually calls the Python function, calculates the result, which happens to be 37.23, and finally feeds that resulting number right back into the LLM. But wait, how exactly does that answer get fed back in? Well, to process the output, we use this incredibly clever formatting trick in the conversation history. We take the messages array, append the tool's JSON output, and we literally pretend the assistant executed the tool call itself. We assign the role of assistant to the tool call and the role of tool to the output. We have to do this little trick just to maintain the conversational flow. The LLM is basically tricked into believing it did all the hard work, having no clue that an external script just stepped in to save the day. By feeding that updated message history back into the system, the LLM seamlessly reads the tool's output, that 37.23, and integrates it into a completely natural, conversational answer for the user. It just confidently says the answer is 37.23, as if it knew the math all along. And what's wild to think about is that every single time you see a model give you an instant math answer or pull up a live web search, this exact, invisible, highly orchestrated dance just happened in milliseconds right behind the scenes. So, how do we actually teach them to do this? Let's look at Section 4, Learning by Example. The absolute simplest way is called in-context learning. It relies totally on the LLM's natural knack for pattern recognition. Instead of retraining the model, we just copy formatting examples and manually drop them into the prompt. It's essentially like giving the AI an open book test. The model isn't permanently learning how to use the tools, it's simply copying the cheat sheet we slid into the prompt window. We show it what a good tool call looks like and rely on it to mimic that behavior. By slipping in a few fake previous interactions involving multiplication and division, the LLM catches on instantly. When the actual query arrives, what is 5.1 times 7.3, the model looks at those previous examples in its context window and knows exactly how to format its response with the proper JSON structure. It's learning entirely from the context we just provided.
But what if we have dozens of tools? That brings us to our final section, Section 5, Training for Autonomous Action.
You really don't want to clutter up your valuable context window with endless examples, because honestly, too many instructions can actually degrade the model's performance. That's where Supervised Fine-Tuning, or SFT, steps in. If in-context learning is an open book test, Supervised Fine-Tuning is like sending the model to a trade school. We train the LLM on a massive dataset of correct examples so that the knowledge gets permanently baked into the model's weights. It natively understands how to use tools without needing a cheat sheet. This is a technique that was really made famous by models like Toolformer.
Let's look at how smooth this can get with inline action. Unlike previous examples that have to stop completely to output a big block of JSON, Toolformer starts generating standard text, right? But then, right in the middle of a sentence, it realizes it needs a calculator, so it outputs a special open bracket token, literally pausing its own thought process midstream. Next, with the text generation on pause, it picks the calculator tool and passes the exact arguments it needs, the 5.1 and 7.3, right there in the middle of the sentence string. This is a massive upgrade over the previous method. It saves time, computes faster, and perfectly mimics how a human might briefly pause mid-sentence to punch numbers into a calculator before finishing their thought. And here is the magic. The external system pauses the LLM, runs the calculation, drops the output of 37.23 right back in, and the LLM seamlessly closes the bracket and just resumes writing the sentence as if nothing happened. By embedding the output directly during generation, the model's tool usage becomes incredibly natural.
Finally, if you want the absolute most robust, generalized agents, developers are now turning to reinforcement learning. Supervised fine-tuning is great, but it essentially just teaches the model to mimic examples. And mimicking is kind of like learning to ride a bike by watching YouTube videos, right? Reinforcement learning, on the other hand, is like actually getting on the bike, falling off, and learning to balance. It moves away from mimicking rigid examples and lets the model learn through trial and error, getting rewards when it succeeds. Frameworks like ToolRL use these really simple, verifiable rewards. The model essentially gets a literal thumbs up or a high score when it perfectly formats its JSON and selects accurate parameters, and a low score when it messes up. Over time, the model naturally aligns its autonomous behavior to maximize those scores, learning deep, generalized strategies for tool usage. Which leaves us with a pretty wild final question to think about. We've seen how these models go from trapped text predictors to autonomous agents acting in the real world. But once they perfectly master any tool we give them, what happens to our digital environments when they become capable enough to start coding and executing tools of their own? It's something we profoundly have to consider as this technology rapidly evolves. Thank you for joining me for The Explainer. I really hope this helped clarify the incredible mechanics behind AI agents.